Hi everyone, welcome to Leetcode Biweekly 122. Wish me luck. Um, yeah. By the way, I'm back in college for a bit, so I probably won't be able to do many weekly contests because of the time zone. So it might only be a couple bi-weeklies for a while. Leetcode, can you please load? Please. Thank you. So there's a 1 and 2, which means you always do. Uh, so you can replace two numbers with their mod. Oh, I feel like the answer should always be pretty small. Huh. That seems kind of interesting. Okay, this is a really weird, weird question. Why is this so weird? Okay, this question one's easy. Question 4. Six, 12, 12. Okay, I really want to think about this question. It seems very interesting. Most of the time, if I have two bigger numbers, I can just remove the bigger number. This actually seems quite hard. Why is this so hard? Okay, so we can basically just ignore the first element, and now we need to choose. We need to do like for each subarray of some size, find the k small stuff, which is not that hard. Do I use Python or not? Can k be equal to 2? No, k is at least 3. Okay. Okay. So I need a max PQ, and now okay, I should insert if PQ.size is greater than k. I want to -1 from k as well. Then I want to do pq.top and pq.pop. Oh, I need to be able to remove an element as well. I can do this with my ordered set template actually. I think I want to ordered multi-set. Okay, I want to add this element. I think it should just be I is greater than k. So we have some elements, and then how does the sum update? If, I guess, s of bisects left, okay, if I bisect left and that's less than k, And then I think I should do current is plus is equal to nums I and minus s dot my brain is not thinking well. S dot find by order k. Yeah, okay, I think that works. Here, if I is greater than or equal to distance, then okay, this feels very dodgy to me. Yep. I think let's increase distance by 1 as well. 3, 16, 13. Okay, so that's like, obviously it's wrong, but how do I do it? Five 15 36. Okay, that's correct, but how correct. I'm not sure how confident I am that's correct. That's fine though. Let's look at this question. Okay, so if there's only one unique small element, the answer is definitely 1. Like, one of my ideas is it's the number of smallest elements divided by 2 and rounded up. Like, that's one of the ideas I have, but whether that's correct, I don't know. Okay, it's definitely not correct. Because for example, if I have like 2, 2, 4, 5, I can do like 5 mod 4 to give me the 1, and then the 2's can disappear from the 1. Oh no. Actually, yeah, the 2's will be able to disappear from the 1. This is really difficult. Okay, I need to think a bit more. Select 2 indices. Okay, I think maybe we care more about the GCD. I think we can do it like this. Like this is like 0 for I and nums. G is equal to GCD G and I. And then if G is less than the minimum of nums, then the answer is always going to be 1. Otherwise, you can't make anything smaller than the minimum. Then we should get, I guess, the count. I need to think this a bit. I still need to think this through. think those will give me zeros still. Nums dot count min nums. Now I can kind of pair these up like that. Like that is correct on the sample, but is it actually correct? I think it is correct. But it's very not clear. We can swap two adjacent elements if they're the same. Okay, for I want to see the leaderboard. False, true, false. Okay, that's not correct. People have finished. Let's just submit. Okay, at least I didn't get any wrong answers. I didn't win because this guy was very fast, but at least I didn't get any wrong answers. I thought this was a very difficult round, and I am proud of myself still, because it has been a very long time since I've done anything. Also, like, I risked it because I'm very close to first place. Okay, let's walk through the solutions. Okay, I thought this was very difficult. Even for problem 1, it's quite hard. We can just brute force always to divide it into 2 subarrays. Into 3 subarrays, but like exactly how you might go about that is slightly difficult. What's instead easier is to notice that the answer is always the sum of the first element, because the first subarray must start at the first element, and 2 other elements, which will be the starting elements of the second and third subarray. For example, yeah, if I have this subarray, and this subarray, then it's the sum of this 1, this 3, and this 12. So really, it's the answer is the sum of 1 and the 2 smallest elements from the rest. I actually just brute force all other pairs, but of course I could just like do something like return num 0 plus sort, like something like that would probably pass as well. Yeah. Hopefully make this make sense. Okay, this question's like, we kind of want to divide it into adjacent. We want to first divide nums into groups with the same bit count, number of set bits. And for example, here we would divide it into this subarray and this subarray, because this subarray all has the same number of set bits, this subarray all has the same number of set bits. And then once we've broken it into subarrays, we're allowed to swap adjacent elements, which essentially means we can sort this subarray using something like bubble sort. So once we've broken down into subarrays, then we can just sort them and then put them back together. So here's how my code works. Like for a given L, we kind of find the largest R such that this subarray from L to R has all the same number of set bits. And that kind of finds this maximal subarray with the same number of set bits. Then we sort it and kind of proceed, and then we check that the result is sorted. Okay, this question is extremely difficult. And I'm actually surprised. Yeah, I'm a little surprised it gets AC, but okay. The main observation is like if you have two elements that are not equal, say like 4 and 7, we can use the operation to get rid of the larger element, because if we just do 4 mod 7, we're just going to get 4 because it's a smaller number. So whenever we have two non-equal elements, if we kind of apply the operation like this, it's essentially equivalent to just removing the largest element. So one strategy, for example, is like if you have like some list like this, like one possible strategy is we can get rid of this 4 by applying this operation with this 3 and this 4. We can get rid of this 4 because we can just do what I just described. 3 mod 4 is 3, so if we remove a 3, remove a 4, and add back a 3, it's equivalent to just removing the 4. And similarly, we can get rid of this 6 and this 8 because they're bigger than, because as long as it's a smaller number, then we can apply the operation. And then now once we have all of the elements of the same length, now we can just kind of pair them up, because whenever we do an operation with two equal elements, we end up with a 0, because 3 mod 3 is 0. So we will get a 0, and we would have a leftover 3, and that would be our answer. And in general, like if we have n elements of the same type, we would get ceiling of n over 2 remaining elements, because if it's an even number, then we will just get like half that many zeros, but if there's an odd number, then we'll get one extra on the end. Okay, but how do we show that this strategy is optimal? Well, it turns out it isn't optimal, and here's one counter example. It isn't optimal to get rid of the 4s and 5s. More like this. If we apply a strategy that I just described, we would get rid of the 4 and the 5, and then like kind of pair these 2s up, and we would end up with 0, 2. But it's actually possible to get it to length 1. Specifically, if we do 5 mod 4 is 1, then we would get 2, 2, 2, 1. And now that this 1 is smaller than all of these 2s, by that operation, we can get rid of all of these 2s. Okay, so it turns out that if it turns out there's a very smart thing to do, and it's dependent whether all of these elements are multiples of the smallest number. Or the equivalent formulation which I've gone with here is if the GCD of all numbers is less than the smallest number in nums. If this is the case, as it is here, then we can take some subset, some subset of nums that contains only unique elements, and the GCD of these elements is smaller than the minimum in this list. Say, for example, this 4 and this 5, their GCD is smaller than everything in this list. Then doing something very similar to the Euclidean GCD, like you might notice that this is basically how the Euclidean GCD algorithm works. And in fact, we can actually apply, we can apply these operations to get the GCD of all of those elements that we just computed. And if this GCD is smaller than these remaining elements, then the answer is 1, based on how I described it before. Like, hopefully that made sense. This is a bit hand-wavy in my head, because I didn't really think about the implications too much. But I'm pretty sure it's something similar to this. You can get the GCD smaller than all other elements, and then remove all these elements by the operation and get an answer of 1. The other case is when like all of the elements are like multiples of the smallest element, in which case we just apply our strategy where we just remove all of these bigger elements and then pair these ones up. And in that case, the reason why that's optimal is because all of these elements would be multiples of these ones. If we ever do like 12 mod 4, we're going to end up with a 0 for each of these, like for each of the smallest elements. If we do it the other way around, we would end up with a 0. And so the answer would actually be equal to, I guess, the number of smallest elements, whereas our strategy gives the number of smallest elements divided by 2. So that's why this is optimal. Okay, final problem. It looks like a really weird condition why we use the second subarray and the kth subarray, but again, it's because the first subarray must start with the first element. So in fact, what I just do in my solution is like I just ignore the first element and then I'll add that on at the end. So what we really need to do is we need to, like, let's just remove this first element, pretend it doesn't exist. Then we need to choose k-take-1 elements that are within some distance apart with the minimum possible sum. And what I do instead is I kind of, once I've removed this element, I kind of want to consider all subarrays of size distance, technically distance plus 1, all subarrays of size distance plus 1, and I want to consider for each of these subarrays what is the sum of the k-take-1 smallest elements, and if I can get that sum, then the answer will just be the minimum of that across all subarrays. So it's kind of like a sliding window type thing. Like for example here, distance is 3, which means it's kind of 4 elements apart because the distance is 3. But it would be like ignoring this one. For all subarrays of length 4, I find the 2 smallest elements and like kind of sum them together. And then the minimum of that across all subarrays is the answer. So with our sliding window, we basically need to be able to add an element, remove an element, and keep track of the sum of the k-take-1 smallest elements. That's basically what we need to do. So here I just like minus k and increase distance just to help me a bit. Just like some off by 1 things. And specifically, I kind of just maintain all of the elements in this window inside a ordered multiset, which here I'm using a custom like order statistic tree. In Python, this would be a sorted list. It has to be a multiset because there can be duplicate elements. And now we kind of either like when we expand our window, we add our current element, and then when our window is like greater than size dist, then we need to remove the leftmost elements. The only question is, how do we maintain the current sum of the k smallest stuff in this variable current? Like, how do we maintain that as we add or remove elements? Let's start with adding an element. If we're adding an element and the new size is less than or equal to k, then we just add it to our answer. Otherwise, there's kind of a special, there's only one situation in which this answer would change, and that's like, say for example k is 2, k is 3. Say we have something like this and we insert an element here. If this element is now within the k smallest elements, then this element kind of replaces this element, which gets kicked out of the k smallest. So that's why we increase by this current element and decrease by this element that was kicked out. And here we update our answer. We find like current, because best is the minimum across all subarrays, so we just update that answer. And here is where we might need to remove an element. And again, there's only one case where the answer might change. And let's say, again, k is 3. And let's say we want to remove this element this time. It's very similar. Like now this element, which was just outside the k smallest, gets added, and then this element gets removed. So that's how we update our answer. And that's pretty much it. All these operations are in log n time, so the total complexity is n log n. This isn't close to time limit, is it? You can kind of check. Yeah, okay, I should be fine on the time limit. I definitely wanted to go with C++ because I'm always scared about the TLE. Okay, let's check the final rankings. It wasn't so good. So I guess that's 5th place, which I don't think is... Oh, I think there might also be China people. So one person in China beat me as well. So I think that's sixth place overall, which for my rating is best sixth place will give me like 5 rating points, I think. I think it would be a negligible amount. Um, it's pretty much balanced because that's my expected position. So Neil Wu, I guess, will reign supreme for another 2 weeks because obviously I won't be able to compete. I won't be able to compete again until like 2 weeks because of the time zone. Anyway, thank you so much for watching, and I'll see you guys next time.